Well, hello and welcome back. Um, I've, we're going to spend some time this week talking about the mathematical models for epidemiology, which is a word I can't say slowly. So whenever I say epidemiology, I'll have to say it quickly. Um, I'm also going to change how I made these videos. I was thinking about some of the comments in the last discussion forum, and I'm glad this is making sense to you and that it's relevant. And I realize that I'm still trying to play teacher. And what I mean by that is that if I were designing a fall course around the COVID-19 pandemic, I would lay out all my information, I would think about the lessons and how they build on each other and all that sort of stuff, as if I knew everything in advance. I don't know everything in advance. I'm a mathematician, not a epidemiologist. Um, and so I'm going to be a bit more transparent in how I'm making these videos. For example, today is March 31st. It's a Tuesday. So this is almost a week before you'll see this video. And I'm going to make these videos during the week as I learn something new, as something occurs to me. And so they'll be a bit more transparent and a bit more honest. For example, at some point in this lesson, we'll talk about mortality rates again. I learned a whole bunch about estimating mortality rates and various types of mortality rates in pandemics. We're all learning together. And what I want to do is be honest about what I don't know and about how the mathematics that I do know informs how I read this material or what do I infer from it. It's just a point of view, of course. And so to kick that off, I've been thinking about exponential growth quite a bit. And I want to show you some algebra. A lot of it you're not going to have to do. And I'm going to show you how to build a better model in a spreadsheet, even though you won't have to do this. And we'll use it to make better predictions. And we'll talk a little bit about predictions. And that'll be the start. So, in Maine today, Tuesday, March 31st, we've passed 300 cases and we've had 5 deaths. Now, it's usually around now that exponential growth really starts picking up. At this point, New York's got like 75,000 cases. The world has 860,000 cases. You know, Even a 10% increase per day at this point adds up really quickly. So I thought we'd revisit this, and what we've been doing is just using 2 data points to construct an approximate exponential model, and we can do better. So let's walk through that. The sort of exponential equation you would have seen in an algebra class has this funny little e, which is like 2.718 whatever, or 2.728, I don't remember. It's some long decimal. It's like pi. It's an irrational number. It's a transcendental number. You have some initial amount, maybe a population. T is your variable. It's time, 1, 2, 3, 4, 5. And then R is some number that controls how quickly your population grows. So this is the sort of thing you see in like a pre-calculus class or algebra class. And it's a curve. And so if we have data, and the data looks like it might be exponential, how do we find out if it is? And if it is exponential, how do we find R? And if we know what R is, how do we find the growth factor? R is not the growth factor, but e to the R is. And that's something we can calculate really easily. So I want to go through and show you how we can turn this into a line and how we can do that, how we can use that in a spreadsheet. So I'm going to, in a minute here, put some equations on the screen, and you're not responsible for them, but I want to show you anyway. I think a bunch of you can follow along just fine, and then we'll see how this actually comes into use, using data, using a spreadsheet to make predictions. So I'm going to use the natural logarithm, ln. I'll take the ln of both sides, and I'm going to do some simplification using properties of logarithms, the log of a product, is the sum of logs. Log is the inverse of e to the stuff. And what I get here, this last line, and again, you're not responsible for this, so you're not going to have to do this part. This last line here is the equation of a line. It looks really kind of intimidating, but this is essentially y equals mx plus b. So this ln of p naught business, this is just a number. This is like our y-intercept. T is our variable, that's like our x. And r is our slope. And then this is our y value. And so what this does is it means I can take data that I think is exponential, take logs of stuff, plot it, and if it's a straight line, the slope of that line will be this r. Let me show you what I mean. So I have a spreadsheet here, and I should say that in the slides there's a link to the data, and of course every day it's updated on the main CDC site, and there's a link to the spreadsheet that I'm showing you. So I went back and found data going forward. So we can start with the 13th of March was the first confirmed COVID-19 case. And then these are confirmed cases. They're a little different than the data I've used in previous slides, which include confirmed and presumptive. And so what I would do then is I would, in my spreadsheet, I would take the ln of the total cases, and I can fill this up really easily. And I have a bunch of numbers. These are my ln of y's, if you will. These are my times. And so what I want to do is I want to plot these two things on a graph and see what I get. So I'm going to have to mess around with it because it never quite knows what I want. There we go. All right. So this log here is the log of the total cases. Logarithms. Who knew? And what I'd like to do is I want to add a trend line. So I'm just in Google Sheets right now. So we all have this same tool. I'm going to do a linear fit. I'll show the r squared, and I want to use the equation. And so what this is telling me is that the best fit line for this has a slope of 0.25 and an r squared of 0.834. That means this data is linearly correlated. It's a pretty good bet it's linearly correlated. And this 0.25, let me go back to the slides and show you how we calculate a growth factor with that. All right, so how do we get the growth factor from this little r thing? So we get r from the slope of the trend line. This is that funny number e that I was showing you a moment ago. Where is it? Yeah, this little e here is a special number. It's this thing. So if you have r, if I give you r, if you find it from a regression, then you raise e to the r, and that's the growth factor. So in our case, right, we did a regression on the data we have. We have a 0.25 value for r. And again, don't worry about this spreadsheet. If you're not familiar with spreadsheets, you're not going to have to do a spreadsheet, but this is how we can do it. And e to the 0.25 is 1.284, which is a 28.4 daily increase, right? So now, again, this is approximate. It looks like it's tapering off here, so the growth rate is a little less. Now, part of that could be these initial outliers. Now, why is it different? Testing. Maine still only has enough supplies as of Tuesday, March 31st, to conduct about 3,000 tests. There's various chemicals you need to do the test. We have a limited supply of them. So testing is being done very carefully. So as we test more, we might find more. Maybe we weren't testing very many before. There's a number of explanations. If we would eliminate these two, um, right? If I were to eliminate these two, what happens to the line? It changes to a 0.184, right? Which is probably closer to what's actually happening. You can see the R squared value is 0.95. So these initial two cases might have just been flukes. These points right here seem to be fitting on a line a lot better. So let's look at this 0.184 and go back to the slides and also do a calculation for that. Right? I'm going to pause to just catch up a little bit. All right. So when I did that, when I took the 0.184 and I took e to that power, I get a growth factor of 1.2. So it'd be 20.2% increase. And so, you know, from now, if I wanted to think about what a prediction would be on the day that you can first view this video, right? So what's that? That's next Monday. So it's 1, 2, 3, 4, 5, 6. So 6 days. So what I would do is take the number of cases right now, 303, times this growth factor, and I would raise that to the 6th power and see what that prediction is. So let's see what that puts us by the time you view this video. That puts us at about 914. That's going to be the prediction I make in this video. 914 total cases as of Monday, April, what day was that again? April 7th. Now, how likely is this to be correct? Well, in preparing these slides, I had gone back to the first week, and I noticed that I had, this is using data from the deaths from COVID. Now, for this particular model, I do have a spreadsheet. This is a graph from one of my spreadsheets using the total deaths in the US from COVID-19. And I didn't keep it up. This stops like last week. And I noticed that I had made a prediction for March 26th, and I had a growth factor of 1.25. So you've seen these slides. Well, March 26th, how far is that till today, right? So 1, 2, 3, 4, 5. 5 days in the future. So what if we took this number, 1080, and moved that forward in the future? So 1080 times a growth factor of 1.25 raised to the 5th power. So that's 3,295. It's about a little less than 3,300. So going to the US, what are we at? At 3,867. So you can see with a more robust regression model, and it's the same sort of model I showed you for Maine. In fact, let me dig out my spreadsheet. All right, so I paused it and I brought up my spreadsheet. You can see that, so this is the same sort of thing. This is a logarithm. I'm taking the logarithm of the total of cumulative deaths, and so that's the vertical axis, and the horizontal axis are days since March 2nd. And I stopped putting data in here on the 27th of March. And so when I graphed this data, and I showed you not quite this graph, I showed you the curve, but this is that straight line model, that linear regression. And I have an R of 0.216, if we were to quickly try to find the growth factor, 0.216, it gives us a 1.24. So it's a 24% increase per day in deaths. That growth factor fits with an R squared of 0.98. So an R squared of 1 is a perfect correlation. So 0.987 is very good. So what does that mean? Well, it was a very good, so it's a very good fit, and it's not surprising. Going back, 5 days, um, the estimate of 3,300 is pretty close. It's unfortunately an underestimate as to the total number of deaths so far in the United States. So this is the sort of mathematics that you don't really want to be right about, and it's comforting in some ways, and it's also maybe more deeply terrifying in others to do these calculations and look at projections. Here's another resource that's linked in the slides that you're looking at, and in the video for YouTube last week, you saw some of these diagonal lines. And what do these things mean? This is on a log plot. You can tell it's a log plot because it jumps. It goes from 100 to 500, then jumps to 1,000, and then 5,000, then 10,000. Things are squeezed together here, and that's characteristic. So these straight lines are different types of exponential growth. So this dotted line is doubling every 2 weeks. This is doubling every week. This is doubling every 3 days. And these are cumulative cases. Right now, the United States is in between doubling every 3 days and doubling every 2 days. Not as bad as some countries like Turkey, not nearly as good as some other ones, say like Singapore or Japan. Now, they do have it for states and territories, and Maine is currently doing a lot better than a lot of other states. You can see New York up here, 35% daily. It's pretty much spot on. So, New York, as you know, is not doing great at the moment. Maine's doing better, but keep in mind that it's somewhere in between doubling every week and doubling every 3 days. So still not great. But these straight lines are precisely this sort of thing that I'm talking about in this graph here, where we're looking at a log plot on this one. Now, as far as deaths in Maine go, there aren't very many yet, and hopefully it stays that way. But we could try making some estimates there. So we only have 3 data points so far. So we could add 1 here and 3 here because we don't know any better. And then we could select these. We could do a graph. Actually, I don't want to have this stuff in between. I'm going to do a little edit and start another sheet, and I'll bring back in. All right, I've gone ahead and I've just copied that data over. Now, again, recognizing that we don't have very much data yet. This is good in the sense that we don't have very many deaths yet. We can do a regression. We don't have a lot of data, so we don't want to put a lot of faith in this. But as a preliminary estimate, we have a line. It's a reasonable fit, and we have an R value of 0.42. Right, so 0.42. So now I'm going to go ahead and I'm going to calculate a growth rate for that. I'll pause the video. So if I take that R value of 0.432, and I take that funny E, which has a value of 2.718, whatever. By the way, you don't have to remember this value. If you go into your browser and do E to the power of 1, it's in there, so you can you can have it do this sort of thing. You don't have to write in what E equals. You can just the letter E. Google knows what you mean. Now, a 54% increase in per day is almost certainly too high. But let's make a prediction. So based on that, right now, if we have 5 by this day, right, March 31st, then by the time you view this video, it's 1, 2, 3, 4, 5, 6 days away. Right? So we would have 5 times 1.54033.512 to the power of 6. And let's figure that out. So again, it's the sort of thing where we're not having to do extremely sophisticated mathematics here. And the experts their calculations are only a bit more sophisticated than ours right now. All right, so this is our prediction for total deaths by Monday, April 7th. Now, hopefully this is a vast overestimate, but this is the nature of exponential growth. Things pick up quickly, just as our prediction for almost 1,000 cases by the time you're viewing this video. You can see this so poignantly looking at the total cases right now in the United States. We'll probably break 200,000 by tomorrow, April 1st. And if we go specifically to the United States, go down, we can see, I think I talked about this in lesson 2. It was under 50,000. Now we're at 75,000 in New York. This is the second day of the week. You're currently working on lesson 2, right? So as you watch this, which is lesson 3, I am just 24 hours after I posted your lesson yesterday, right? 8,600 new cases, 1,500 deaths. And if you look down the line here, this is what gets scary. These states, they're a week away from doing the same sort of thing, right? So what's happening here? 2,000 more cases out of 18. So if we have 2,000 divided by 18.6, it's about a 10% increase. So we're talking about nearly a 10% increase. I mean, it's just gonna, it's gonna grow very quickly. So all these sorts of things, if you look back to previous videos, they were much lower just a few days ago. It's right here that things start ramping up, because we're talking about a percentage of, right? 10% more is 20% more. Well, 50% more 5 isn't that much. Maybe we have 7 here, right? Maybe we have 8, 9 here. But 50% more of 10,000 is a lot. So this is how exponential growth gets started, right? Same sort of thing here. Back in the beginning of the cases, there were just a couple cases, but it's already building pretty quickly. Look, an additional 25, another 25. It's gonna be ramping up. So, okay, I'm gonna pause there. It's a little longer video than usual. And we're gonna have some exercises of how to find growth factor from R. And yeah, we'll pause. We'll pause here.